Right. So we are back with Python for engineers once again, and here this is one of the last few classes on this, and today we are going to discuss SymPy. So SymPy stands for Symbolic Python. So here with the help of this package we can do symbolic computations in Python. Okay. And I shall explain what it means when I say symbolic computation and how it differs from numeric computation or rather numerical computations. So yeah, so this is one of the computing paradigms that you have built in within Python. Now earlier before this, if you wanted to do symbolic computations, you only had two options for the most part. Okay, you had Wolfram Mathematica, where you could do symbolic computations, and you had MATLAB, where you can also do symbolic computation. And for Wolfram Mathematica, the primary objective of that software, entire software, is doing symbolic computation. So that's a very good choice if you are doing symbolic computation. But again, the licensing cost for Wolfram Mathematica is like thousands of dollars, right? So you can't imagine if you are, for example, if you're after becoming an engineer, if you're trying to start a startup, maybe you are trying to open your own company in that case, and maybe you are doing scientific computation. If you're on that field, I mean, it becomes really impossible for you to purchase licenses of those software. And MATLAB, it's thousands of dollars literally. So you can understand how this kind of restrictive licensing schemes pretty much stops people from using those software, right? And again, this entire everything that we are going to talk about today, okay, everything, all of these are open source, right? So it's completely free for you to use. You can do any modification you want, okay, and after doing your modifications you can even sell the software. That is how these things are licensed to you. But again, I am not going to burden you with the licensing terms and everything, but just keep in mind that you are not violating anyone's copyright, anyone's licensing. You are not doing anything wrong, anything illegal when you are actually using this software, right? So again, this is a Python package readily available, and if you're using Anaconda distribution, if you have installed Anaconda Python distribution, then you already have this SymPy installed. If you're using Google Colab, then also you have this SymPy installed already, right? And again, just like one of our previous sessions, I have pre-compiled everything here so that I can complete this lecture in a finite amount of time, right? So with that said, we are going to see symbolic computation today, okay? And so far we have seen numeric computation, or rather numerical computations. And in numerical computations, if you recall, what we usually did, we assigned variables with certain values, right? Those values could be Python objects, right? Those values could be any Python object. Those values could be lists, those values could be numbers, okay? Those values could be dictionaries, sets, tuples, etc., right? So when we do those kind of computations, it's called a numerical computation. So basically, essentially, your variable is storing some numbers in some way, right? Some kind of data structure that is holding certain numbers, right? So whenever you are doing computation like that, then it's called a numerical computation, or rather numeric computation. But symbolic computation is different, right? So for example, if I ask you what is the derivative of sine x with respect to x, for example, right? What is the derivative of sine x with respect to x? You would say, okay, cos x, right? But if you are asking a numerical program, a program which can only do it numerically, it will ask you, okay, you are asking for the derivative of sine x with respect to x, but you shall also need to tell me the point at which you want to calculate the derivative. See the point, right? If I ask you what is the derivative of sine x with respect to x, you would say cos x. But if you ask a computer which does everything numerically, okay, what is the derivative of sine x with respect to x, you shall also need to provide the point at which you are trying to calculate the derivative. So essentially you are calculating the derivative here, evaluating the derivative at a point, for example, right? So essentially every variable, so you can evaluate functions at points like that, right? But in symbolic computation, that x is not carrying any value, but instead it is being treated as a symbol, right? So you are differentiating sine x with respect to x, okay, that's cos x. So everything is a symbol. All of these things are symbols, right? So they are not someone is saying, why do I need to give a particular point? Because for numerical computation you have numerical algorithms to calculate the derivative, right? So essentially you take a point, you take the previous point, subtract them and divide it by the step size, something like that. You differentiate like that. So you have something called numerical methods, numerical algorithms, right? Numerical methods. So whenever you do something using numerical methods, it becomes a numerical computation, right? So you have probably studied a paper on numerical methods, right? There you studied how to differentiate, how to integrate, how to do all these things, how to solve differential equations numerically, which means you are implementing a computer program that numerically solves everything, right? Where x is just a variable that has certain values, right? And so far, whatever computation we have seen, we have only seen numerical computation, right? So that variable had certain values, right? That variable had certain values. So that variable was assigned to a certain Python object and like that. Now here, symbolic computation will differ in a way that the variables that I'm going to talk about here would be Python objects themselves, and they would be symbolic objects. So if I say x while doing symbolic computation, that x will be treated as x, not just a value, right? So for example, if I say x equal to 1 and y equal to 2, then x plus y becomes 3. That happens when I do numerical computation. But when I do symbolic computation, x plus y remains x plus y. Okay, so because this thing is being treated as a symbol. So x is a symbol, y is a symbol. So x plus y is nothing but x plus y, right? So you don't have a value associated with x, you don't have a value associated with y, so that when you add them, it becomes another value. It doesn't happen when you are doing symbolic computation. But again, symbolic computation is some sort of a superset of numerical computation. That way, if you want to evaluate something, you can. But if you don't want to evaluate something, you can leave it as it is. So that's the basic of, that's the fundamentals of symbolic computations. And whenever, and in engineering, many times symbolic computation becomes really necessary whenever you are trying to think about, not in terms of what the results are, but in terms of what is the nature of the result, what the nature of the result is, right? So maybe you want to solve a differential equation, but you want to find the answer in terms of a function, right? In that case, you are going to use symbolic methods here, right? Similarly, say for example, you are doing a Laplace transform, inverse Laplace transform, you are probably not asking for particular values, right? You are asking for a particular function in return, right? So you are going to get those here, right? But again, doing programming in symbol, I mean, the way it is implemented inside Python is very different from how things like Numpy, things like SymPy, these things are implemented, right? So this is a very different internal computational architecture, if you want to say so. All right. So again, we are going to use SymPy for doing symbolic computations, right? And if you want to learn more, just do a Google search on SymPy. You would see quite a few. So again, I compiled this tutorial just to make sure that I cover a certain set of topics here and within a stipulated amount of time. Again, I would strongly suggest you open Google Colab, because SymPy is installed in Google Colab. Or if you have a Jupyter Notebook, Anaconda distribution installed, open Jupyter Notebook, you will see SymPy has already been installed. All right, so let's proceed. And again, during the class, if you have any query, just make sure to ask your questions. I shall be definitely answering your questions. Right. So now, look very carefully. Whenever we are doing symbolic computation, more often than not, we are actually looking to do exploratory computing, exploratory programming. What I mean by that is that I'm not looking to develop a big program that does some symbolic computation, right? Instead, I'm probably trying to integrate something, right? So maybe I want to find the Laplace transform of something, right? So again, so that is why, since we are just doing exploratory computing, at least for symbolic, as far as symbolic computations would go, we import these things in this way. So instead of saying import SymPy as sy, something like that, so instead of saying something like import SymPy as sy and then calling everything with sy dot, right? If I import it like that, then if I want to import something, if I want to call a module or call a function from within SymPy, then I have to write sy dot. So instead of doing that, I'm importing everything from SymPy because we are just doing exploration, right? Here we are doing exploratory computing. So if I do that, so every function, every module that resides within SymPy will be imported into my namespace here. Okay, then so these are the standard imports you have to again remember. Okay, whenever you are doing computation with SymPy, then the next import that I am doing is the sympy.abc and import star. So this import here essentially brings all the symbolic functions and everything into my namespace. All right. So like now if I write sine, it will no longer be a numeric function, but instead it will be a symbolic function. If I say cos, if I say e to the power x, etc., exponential, all these functions will now become numerical functions because they have now been imported from SymPy, not from Numpy. Okay. And if I so I have a sine function from Numpy, I also have a sine function from SymPy. They behave very differently. Okay, the functions that come from SymPy, they behave like symbols, not just numerical functions. Okay, and then the next import is also very crucial. So here I'm saying from sympy.abc import everything. This essentially makes sure that all the variable names, standard variable names used in algebra or symbolic computation, x, y, z, alpha, beta, gamma, these things are all symbols, not just numerical variables. So if I do sympy.abc import star, it makes sure that x, y, z, a, b, c, alpha, beta, gamma, all these things are symbols, no longer standard numerical Python variables, right? They are now Python symbols which behave like symbolic objects in conjunction with SymPy. So these two imports are very important. Okay, then I also import these two things just to make sure that I have two very essential symbols like pi, and this is my complex unity I, right? This is the complex unity which we usually represent with j. This is represented with a capital I, uppercase I in SymPy. So these three imports are essential really if you are doing symbolic computation, if you are doing exploratory symbolic computations. Otherwise you could just do import SymPy as sy, things like that, and you could call functions from that as sy dot and things like that, right? And then I also import these. Okay, I also call this function, and this actually comes from the SymPy module. This makes sure that everything is rendered through mathjax, something called mathjax, so that the mathematical equations look like mathematical equations. Okay, so this is for rendering things properly. Okay, and I'm not currently right now I'm not using Google Colab just because this thing doesn't work properly in Google Colab. Somehow the results that Google Colab generate, I mean, looks poor. Okay, the rendering is not that good. The mathjax rendering is not that good in Google Colab. I'm sure there might be a workaround, but I did not look for that. So let me compute that. So I have successfully computed this. Fine. All right. So we have imported all the modules that I needed to. Right. So now let's say what I can do with this. Okay. Right. So of course now say look at this one. Okay. So this is cos x plus 1. It's a very simple thing, right? And I'm assigning that to a variable name. So this is a variable name, right? So imagine this is y. Okay, so y is equal to cos x plus 1. Now this is not going to look for a certain value of x or a certain array for x like that. It won't be looking for that. Instead it will represent symbolically as y equal to cos x. So y is essentially cos x here. All right, somehow it is not rendering it properly. Let me just hold on for a second. All right. Right, so I think you can see the results, right? So now I can do computations like this. I can say Okay, fine. What if I want to do something like this? Y plus 2 whole square. So this is again the whole thing squared up, right? So it won't be computing at a certain point, but instead it is going to generate a result that looks like this. Unfortunately, rendering is not okay. Something is going wrong. Hold on first. Just let me restart the camera. All right, let me start it. No, just the problem is that I want to see. I mean, these results are not being properly displayed. There is a problem with the display thing. Okay, let me just get rid of this entire thing. Okay, that is. Just hold on for a second. Just hold on for a second, huh? Because things are not working properly, unfortunately for me. So you are going to see how I troubleshoot things. So the Rise I installed probably is not working. Just hold on for a bit. All right. Let me see if I can run this once more. All right. Hold on for a bit. If I remove this one, does it work now? Unfortunately, it does not. Hold on. So it is having issues with rendering things properly. Nice. Okay. So we have to make do with these things. Okay, all right. Fine. Let it be into the none. All right, so I think this is now fine, right? There is no issue with this. All right, so we were actually having certain issues with the rendering scheme here. All right, so again, these are the standard imports. Sorry for the interrupt here. Okay, all right. So now we can assign declare variables like this. So essentially, this is treated as all these functions and everything, these are treated as symbols. So y is not being evaluated at a point, but instead y is being assigned to 1 plus cosine x, right? 1 plus cosine x. So if I say y plus 2 whole square, then y was essentially cosine x plus 1. So we are adding 2 with that, so it becomes cosine x plus 3, and then that's a whole, there is a whole square, right? Then something like that. So instead of writing y, so let's say axpr. So that was the expression, right? So that was my expression, and say, right? So like that, right? So again, this is being treated as symbols, right? Now we can substitute particular values, okay, particular variables with certain values or other variables. So here in this expression I had, this expression was essentially cosine x plus 1. So instead of x, I can write some other variable or some other values or some things like that. So, so this was the expression. Again, hold on for a second. This was the expression. And if I say, this is not correctly working somehow. Okay, this is not correctly working. Okay, forget about this one. Okay, and look at this one. Fine. So it's not correctly working because I just messed things up. Let me start the kernel because, hold on. So once again, let's restart. Okay. So this was our expression, and if I add something and make a whole square, and this appears like that, no problems, right? Now if I, now this was the expression, right? So this was cosine x plus 1, right? Now if I substitute x with y, see, this essentially becomes cosine y plus 1. I can, if I substitute this with 1, then becomes cosine 1 plus 1, something like that, right? So if I substitute with it with some other variable, then it becomes like that. But imagine, but remember that x, y, all these functions, everything are symbolic variables. This x, y, these variables are symbolic variables because I did do this import, and all the functions are also symbolic because of this import here. For example, now here I can replace x with pi, for example, and this was cosine x plus 1. So cosine pi is minus 1. So if I substitute x with pi, then I get to have this, something like that. Okay. Now let's look at this substitution. So right off the bat, what we are showing you is that whenever we are doing symbolic computations, we also have the ability to do numerical computations, right? So for example, here is another expression for you, right? So this is x cubed plus 4xy minus z, right? So if I want to leave it as an expression, I can leave it as an expression. Just to show you, if I want to square this expression, that would be the square. This is the square, right? But the thing is, if I want to leave it as an expression, it's fine. But if I want to evaluate this expression at a point, I can also do that by using the subs method. See, I did the substitution using, by calling the subs method on the expression variable here, and on the expression variable here, if I do the subs method here, so what I can do, I can pass in a list of tuples here. So what I'm saying is that, okay, now on this expression, x has a value of 2, y has a value of 4, and z has a value of 0, and evaluate the values. So it evaluates everything, right? So I can do this kind of substitutions, right? So if it's a function of a single variable, then I can just say the expression dot subs and then name of the variable and the value I want to evaluate at. And if it is a function of multiple variables, then I can evaluate it like this, right? So that's the first thing you should know, that a symbolic computation is a superset of numerical computation. So you can do numerical computations just like that, right? So now rationals. So what are rationals? Rationals are proper, or rather perfect representations of fractions. So if I do something like this in pure Python, what happens is it is 2 divided by 5. That's just 0.4, right? But this is a floating point representation. Okay, this is just a floating point representation. Essentially, this is an arithmetic representation, right? So this is how computer stores numbers. This is an arithmetic representation. But if I do something like this, then this essentially becomes, see, this is written as 2 by 5. This is a rational representation. This is an exact representation. Okay, do you understand the difference here? So if I say, for example, if I say 1 by 3, and of course Python is writing it as 1 by 1.33333, but you can write as many 3's as you want, but the representation will never be complete, right? But the representation will never be complete, because this thing will never be exactly equal to 1 by 3. This will become closer. This will grow closer and closer to 1 by 3. Okay, this will come closer and closer to 1 by 3, but this will never become 1 by 3, because you can write as many 3's as you want, but this never becomes 1 by 3, right? But for rationals, if I say 1 comma 3 here, essentially this is a rational representation. This is exact representation of 1 by 3. Now this kind of exact representations are often important while you are doing numerical computations. All right, whenever we are, so symbolic computations, right? So this is being treated as a symbol, right? Because try to understand, if I have this, so for example, if I take this result, say for example, if I say x equal to this, okay, x equal to this, and say if I multiply this with 3, okay, I'm getting fine, right? I'm getting 1, because that was the representation here. But see, say if I say if I want to find 1 by 3, okay, and if I take this number and multiply with it with, say for example, say, let me just reduce the, so now this is sort of a representation of this, right? So if I do something like this, what happens? Of course it is not exactly equal to 1, right? That's the unfortunate problem here, right? But if I do take these values as rationals, then what happens? This is an exact representation, right? And again, this nature of exact representation would be evident later on, right? So again, for exact representations, if you're doing numerical computation, if I write pi, then pi will be just an approximation, right? It will be 3.1415, things like that. Okay, it will be an approximation. But if I write pi while doing symbolic computation, it will be an exact representation, exact symbolic representation of pi, right? So you can imagine however many digits you want, in a sense, right? So this is again just another example here. Again, look very carefully. This I is just the complex unity here. So this is just a representation here. Again, I made sure that this y was wrong. So what was it? Okay, unfortunately I considered something to be y. Okay, unfortunate. Let's just say z. Fine. And I wrote x, right? Okay. All right, say something like that. Okay, again, it's a symbolic representation, right? I can evaluate this symbolic representation. I can evaluate this at a certain point. So for example, I can, if I want to evaluate this symbolic representation at a certain point, all I need to do, I need to substitute these variables with values, right? Using this subs method here, right? All right. Now SymPy gives you a function called SymPy. Okay, so stands for what should I say? Symbolic Python 5, for example, right? So it's a SymPy. So SymPy function converts any string, okay, or other standard functions into SymPy functions. SymPy functions. What are SymPy functions? Again, symbolic functions. So for example, here is a string. It's a Python string. It's a valid Python string, right? Now, if I call this SymPy function on this string, then it becomes a SymPy expression here. See, it's a SymPy expression, for example, right? So this was a string, and this string has been now converted to a SymPy expression. For example, look at this one. This was 2 by 5. Now, if I say SymPy on this string, it becomes a symbolic expression. And when it becomes a symbolic expression, I can evaluate it at a certain point. So for example, if I want to evaluate this expression at x equal to 2, I can always call the subs method and evaluate this. Evaluate this expression. So hold on a second. So this was the expression, and if I want to evaluate this at a point, I can evaluate this. But unfortunately, this x was no longer a variable, right? Let me just do one thing. So since he assigned x, so it became a problem. So right, look at this one. So we substituted x with 2 and we have this value, right? It's a very simple expression. All right. So now let's see again. Let's look at evaluation again once again. So for example, here is an expression, square root of 8. So you know that would be 2 root 2. Again, root 2 is an irrational quantity. If I ask you what is the value of root 2, you would have to give infinite number of points, right? It's an irrational quantity, right? So again, look very carefully. If I write square root of 8, again now this result that I get is an exact representation. Okay, it's an exact representation, and since it is an exact representation, I can choose as many points as I want to evaluate while evaluating it. Okay, so if I want to evaluate it up to a certain number of points, I can do that. But what if I want 100 digits? I can do that. I can just call the eval function. Okay, so eval function evaluates an expression. So this is again an expression where there is no variable, right? All these values are there. Now I am evaluating this numerically. So again, look very carefully that there is a certain difference here, right? This is a symbolic representation. This is a numeric representation, right? Both of them are representations of square root of 8. This is an exact symbolic representation, which is 2 root 2. And this is a numerical representation up to a certain decimal point. And if I want to increase the number of decimal points, I can do that by saying the number of points I want. Just to show you a pretty example here. So of course I have something like pi. Okay, pi is pi. But what if I want to evaluate pi, or rather I want a numerical representation of pi? Okay, this gives me a numerical representation of pi. But what if I want 1000 points, 1000 decimal places, rather 1000 significant digits in pi? Now look very carefully. So this is 3.1415 and so many digits of pi. 1000 digits, right? This was possible because pi was represented symbolically. This wasn't represented numerically, right? So whenever you want to evaluate something, you can evaluate it, okay, up to any amount of precision you want, right? So this is essentially giving you infinite amount of precision whenever you want to have it, right? But if I import pi from Numpy, in that case, it will be just be a double precision floating point number. So only 64 bits of memory will be allocated as floating point number. So it will be a double. Okay, so pi will be stored as a constant that has a 64-bit storage capacity, right? So 64-bit floating point number. And you'll be able to store these many digits, like 15 or 14 digits, something like that, maybe something like that, whenever you are dealing with NumPy. But again, NumPy has its own advantages, but because whenever you don't need this much of precision, or whenever you can get away with not representing everything exactly, you can use NumPy, because NumPy is pretty fast. But whenever you need exact representations or symbolic computations, you would need this. All right. Okay, there is just one more example. Sometimes doing subs is not enough. So this is an expression. So this is sine 2x plus cos 2x. If I say subs x comma 2, what happens? X is replaced by 2, but unfortunately it is not evaluated. See? So this becomes sine 4 plus cos 4, but this is not evaluated. But whenever I want to evaluate this, all I need to do, on this expression, I need to call eval in conjunction with subs. So this is again another syntax. When sometimes what happens is that this substitution does not result into a perfect evaluation, right? So if I put 2, then SymPy needs to do some sort of computation and some sort of what should I say, finite computation here, right? So if it cannot do that, in that case it leaves the result as it is. So it writes sine 4 plus cos 4. But if you want to evaluate this, you need to use this syntax, this particular syntax. So you have to use eval in conjunction with substitution in order to get the output as desired. So it will now evaluate sine 4 plus cos 4 and it will give you result like that. So again, we are just showing you how to evaluate things. So this is the end of numerical computation. So far what we have been doing, we have been expressing symbolic variables, symbolic functions, and we are evaluating them at certain points, right? We are done with that. Now let's do let's do algebra. Okay, let's say algebra and trigonometry, things like that. Now let's do symbolic computations, right? So this is what is this? This is sine square x plus cos square x. Now we have a function, SymPy function called simplify. So if I say simplify, it does simplification for us. Of course, sine square x plus cos square x is equal to 1. So if I say simplify on this, it gives me 1. It does not ask me, okay, at what point do you want to calculate it? Okay, but instead it gives me a symbolic result. This 1 is also symbolic. This is not a numerical result. Okay, because this is an identity and this is equal to 1 no matter what the value of x is, right? So this is an identity. So this is simplified to an identity, not evaluated to 1. You understand the difference, right? This sine square x plus cos square x is identical to 1. This is not equal to 1, right? So we are not evaluating it and finding out, okay, it's 1, right? It's not like that. It is identical to 1. So no matter what value of 1 you put here, x you put here, it will always be 1. So this is going to give you simplified identities, right? Let's say another expression here, right? So again, what we are doing, we are writing an expression like this. So essentially x cube plus x square minus, again, you understand the representation cube here, right? So this is star is power in Python, of course. So x cube plus x square minus x minus 1, and then on the denominator I have x square plus 2x plus 1, like that. So that's the expression here, right? So if I call simplify on this, what happens? It removes common factors. For example, there would be common factors, okay, and this entire denominator is a common factor, okay. So what happens is it factorizes and cancels out the common factor. But whenever it does that, yeah, Google Colab might give you some erroneous results, right? So this is being given as 1.10. What? No, Google Colab cannot give you 1.10 for this one. This has to give you 1. Just one more thing, run this one. So if you are following it on Google Colab, just run this once more, because I made a mistake and wrote x equal to something. I wasn't really supposed to do that. So x was assigned a variable and it might give you some errors accordingly. Okay, so like that. Okay, so now if I do simplifications like this, it happens to be this one, right? Right. Okay, just like simplify, you have a function called expand. Okay, let's just look at this one. So this is x plus y plus z whole to the power 5, and if I expand this, this is the expansion. Okay, just to start with basic examples, let's say a plus b whole square. Let's figure out the formula for a plus b whole square. Nice, that a square plus 2ab plus b square, that's fine. So what about a plus b whole cube? That's fine. A cube plus 3a square b plus 3ab square. Oh, if it is giving you 1.0, then it is doing a numerical computation, which means that you already have x assigned to a variable, x assigned to a numerical variable. So I would suggest go back and run this cell once again, this one, so that x becomes a symbolical variable once again. When x becomes a symbolic variable, go back and do this computation once more. You would see 1, not 1.0. 1.0 is not an exact representation. 1 is. If you are seeing 1.0, it's not an exact representation. That is happening because I assigned x to a certain value earlier, right? Mistakenly. So I have gotten rid of that by running this once more. So run this once more, go back, you would see the symbolic result. And try to understand the difference. If it is saying 1.0, then it is evaluating. But if it is saying 1, it is showing you an identity after simplification. There is a difference here, right? Right. So this is a plus b whole cube, the formula for that. What about a plus b whole to the power 4? Just like that. So what about a plus b whole to the power 10? Like that. What if it is not a plus b? What if this is a plus 1 by a? Yeah, we have seen these things. Right? This is a plus 1 by a whole to the power 10. Who knows? Alright. So say a plus 2b plus c, and then 2b plus 3c. Who knows? and then I have a whole to the power 10. So we are just doing tremendous computations here, right? So let's expand this. Okay. Okay. So this is a plus 2b plus 3c whole to the power 10. You can see the power of this, right? This is something huge, but it can do these computations pretty easily, right? So now we are going to the meat of it, right? The actual workings of this, right? So we can expand things like this kind of products here very easily, not just powers. So we have an expression like x plus 2 product with x minus 3, and that can be expanded like that. Again, x is a symbolic variable. If you somehow mistakenly made x a numerical variable, this will become a bad thing, really, right? Again, we are expanding another expression. Just these are just examples, right? Okay. Right. Now, good examples. When you were doing like in your junior high school, so you were doing factorizations, right? So, for example, I am now factorizing x cube minus x square plus x minus 1, things like that. So these are going to be rational factors. Okay. So if I say factor, so again, so you have seen three functions, right? You have seen simplify, you have seen expand, now you're looking at factor. So if I say factor and give it an expression, then it will do rational factorization. Okay, so this is a rational factorization on this. So this is again a very complicated expression. So this is like x square z plus 4xyz plus 4y square z, like that. Again, this is the rational factorization here. Okay, and you can pass in an expression and figure out the list of factors. Okay, so again, so I passed in a expression. So this was the expression I passed in, and I wanted to figure out what were the factors. So it says there is a factor of 1 and there is a factor of z, but this appears once, and there is a factor of x plus 2y, but this appears twice, because that is true, right? One is a factor of everything, right? So of course 1 is a factor. Then there is a factor z, but that has a power of 1. So this is what it represents. So z has a power of 1. Then there is a factor of x plus 2y, but it has a power of 2. So this is what this factor list function gives you. It tells you x plus 2y has a power of 2, right? Like that. Right. All right. So let me just show you. Now look at this expression here. Hold on for a second. Okay, so we have an expression like this. So x plus 1 multiplied with these and multiplied with this, right? So this was the expression, and I want to expand this expression. Just another example. Okay, and after expansion I want to assign it to another variable and then print that variable. If I do that, this is that. Okay, I think you recall this expression. The original expression was x plus 1 into this, right? And I expanded this and assigned it to a variable expression 1. But what if I want to factorize this? Of course, if I factorize this whole thing, this is supposed to become this thing, right? Because this was the original thing, right? So if I factor this, so this essentially goes back to the original thing, right? So of course, expand and factor, these are just two kind of complementary functions. Expand expands, and factor actually factors out and combines. All right. So you have another functions called collect and factor. You can use factor to factorize, but you can use collect to collect like powers. Okay, just to show you what I mean here. Look at the expression here. So this is xy plus x minus 3 plus 2x square minus zx square plus x cube. Sometimes what happens, you want to collect equal powers, right? So you want to collect all the cubes of x, you want to collect all the squares of x, things like that. So again, just this is a factorization. So if I want to factor this, this is not factorizable, right? In rational factors, it is not factorizable. But what if I want to collect it? So if I collect this, then what happens? Okay, we have an x cube, right? We have an x cube. Then with x square, I have x square z and 2x square. So these two terms, like x square z and minus x square z and plus 2x square, they can be collected. So out of these two, x square can be taken common out of this, and that we will be left with 2 minus z. And out of these two, I have xy plus x. So x can be taken common out of this. So x can be factored out, and I would have y plus 1, and then I have a minus 3. So this can be, alright. So this can be done this way without any issue, I think. Right? So I think you are following along, and if you encounter any problem, make sure to tell me. Now, sometimes what happens is that the simplify function doesn't always work. Sometimes the simplify function is sort of a wrapper function. It tries to figure out how to simplify. But sometimes you know what you are trying to do. Maybe you are trying to cancel common factors, right? Maybe you are trying to cancel common factors. So here there is a fraction, there is a representation here. So this is x square plus 2x plus 1, and in the denominator I have x square plus x. So you know you want to cancel x plus 1. So you want to cancel common factors from the numerator and the denominator, right? So if you already know how you want to simplify it, instead of calling the simplify function, you can call the specialized functions. So you are calling the cancel function to cancel the common factors from the numerator and the denominator, and the result will be x plus 1 divided by x, because from the numerator and the denominator a common factor of x plus 1 will be cancelled out, right? So here is another expression for you. Look at the expression. So this is 1 by x plus, on the numerator I have 3x by 2 minus 2, then again on the denominator I have x minus 4, right? Now if I say I want to cancel these, so it will again try to do some sort of simplification, or some sort of cancellation of common factors from the numerator and the denominator. But in order to do that, it will first combine the factors and then try to factorize the numerator and the denominator and then cancel out the terms. If that is not possible, you would end up with a combined result, right? Something like that. There is just another example for you. So look at this expression. So again, this was just a big expression like that, okay? And I know I maybe want to find out the result after cancellation of common factors, okay? So if I do that, okay, so I have gotten rid of x plus 1 as a common factor from the numerator and the denominator. So that is again, right? So let's just, as an example, if I say simplify on this, okay, it also does the same thing, because simplify can right off the bat figure out what is going to happen here, right? Sometimes simplify cannot figure out. In that case, cancel is a better option. If simplify cannot figure out how to cancel things, or if you are looking for cancelling things, then using cancel is a better option, right? Now, just the opposite. So here we are just simplifying, right? Cancelling terms, okay, right? Combining terms. The opposite of that would be expanding things, right? Pulling things apart. So this function apart does partial fraction expansion. Just to show you an example, imagine this is the expression and you want to do a partial fraction, and you already know what is the best use of partial fractions for doing integrations and for doing inverse Laplace transforms, right? Doing partial fraction is essential. So you have an expression like this and you want to do a partial fraction. What function would you call? You would call the apart function. So it will expand everything in terms of partial fractions. So now you gave it this function, and you wanted to convert it into partial fractions, suitable partial fractions. Okay, someone is asking, why would not simplify be able to figure out some things? Yeah, the problem is, the thing is, so far the examples that you have seen are pretty basic examples. All these things are algebraic variables, right? Even polynomial variables, things like that, right? So yeah, simplify is able to figure out things like that. But if you combine this with exponentials, trigonometric functions and all, simplify might not be able to figure out what you are trying to do. Get the point, right? So you might want to give certain hints to simplify that, okay, I know this is going to happen, right? So this is a simple polynomial algebraic function. There is no issue with that. But if I combine this with combine this with trigonometric functions and all, it might get confused. Okay. In those situations, you might want to use cancel if you want to cancel certain factors, right? Again, your first bet would be to use simplify. If simplify doesn't work, then figure out what you want to do. Simplify works most of the time. Okay. Now let me show you what your question would be answered with examples shortly. Again, look at this one. So this was a big expression here, and this apart function, this function apart, this actually spread everything apart like that. So this was the partial fraction expansion. Of course, this term x square plus x plus 1, again, what happened here is the denominator was factorized, and then after the factorization, okay, numerators were assigned, okay, and accordingly all the values were evaluated, and subsequently this is identical to this. For every possible value of x, this is identical. These two expressions are identical, right? So this is a partial fraction expansion, right? Got it? Right. Now let me show you when simplify actually fails. For example, an example, right? So this is a trigonometric expression, right? So this is sine to the power sine x to the power 4 minus 2 sine square x cos square x plus cos to the power 4x. This expression. I want to simplify this. So instead of saying simplify, now I have to say trig simplify, because if I say simplify, it might work, it might not work. If I say simplify, okay, it was able to do that, but okay, but it is always recommended that you do trig simplify to make sure, okay, trig simp, to make sure that you're telling SymPy that, okay, I know it's a trigonometric expression and the simplification is going to happen trigonometrically, right? So like that. But again, more often than not, simplify would figure out what to do. Okay, if it is failing, okay, if it is unable to figure out what to do, then you are supposed to give it hints. Okay, okay. There is another expression. So this is sine x multiplied with tan x divided by secant of x. So the answer is sine square x. So what if I do simplify here? It might still work. Okay, simplify still works. Okay, again the point stands. If simplify fails, then choose these options. Okay, same thing for using hyperbolic functions here. Okay, now look at this one. If I say expand on this, so what is this? This is sine x plus y whole square. Sine x plus y whole square. So if I say expand on this, now SymPy doesn't know what to do with this. So this is sine x plus y whole square. Okay, so now SymPy does not know what to do with this. It does not know how to expand this. But you have to now tell it that I want a trigonometric expansion. I want the formula for sine x plus y to be written, and then I want it to make a whole square of that. Okay, just to show you what I mean. So if I say this, Python does not know what I mean, because sine x plus y is fine, right? But if I say expand underscore trig, okay, now Python knows that I want it to write out the formula for sine x plus y like that, right? So something like that. A sine, for a sine it doesn't happen. Okay, in any case, say for example, if I say cos, right? If I say tan, okay, look very carefully. So if I say expand trig, now it knows what to do with this. If I just say expand, it would be confused and it will leave it as it is. Okay, if I say expand trig, then it will know what to do. And if I put a whole square out of this, now it will do expansion, complete expansion of this. So it will first do trigonometric expansion, then it will do an algebraic expansion on this, right? So like that, something like that. So after doing expand trig, if I call the expand function, see, it expanded everything. So I first had to do trigonometric expansion, then I had to do generic algebraic expansion. Then this works. I think you understand the point here, right? So let's take the sine thing. Now everything has been expanded. Now look very carefully again. If I just say expand trig, it will do this kind of expansion. So again, it expanded the trigonometric part. So basically sine x plus y was expanded as sine x cos y plus cos x sine y, right? And the whole square was left alone, right? So now on top of that, if I say expand, if I expand the whole thing once more, then it will do an algebraic expansion on top of the trigonometric expansion. So I think you understand the point here. Get it, right? If you have any query, feel free to ask. Okay, I don't have line 86 anymore. Okay, let me show you what I mean once again, in case you don't understand this. So if I just have sine x plus y, I have sine x plus y. If I ask Python to expand this, Python wouldn't know how to expand this, unfortunately, because it is not going to be an algebraic expansion, right? It is no longer going to be an algebraic expansion, right? But if I say expand it trigonometrically, so if I say expand underscore trig, then it's going to expand it trigonometrically, right? Got it? So just to show you, right, it did the trigonometric expansion. But if I say, if I have sine square x plus y, and if I want to do expansion trigonometric, in that case it will expand the trigonometric part and leave the exponential part. So that was the exponent, that was the whole square, right? A square of the whole thing. So it has been left alone with the trigonometric expansion. And with on top of that, if I write the expand function, so if I take this whole thing where the trigonometric expansion has been done, if I take this whole thing and expand upon it, so this will be an algebraic expansion on top of the trigonometric expansion, then it expands everything, right? So this is being treated as a, this is being treated as b, and this is like a plus b whole square. I think I answered your question. So that is again, the expand, the simplify, they might not always work, and if they do not work, yeah, so expand actually expands everything once all the trigonometric and the other things has been taken care of. Okay, so now we are jumping to calculus. Okay, so of course calculus here would start with derivatives. It should have started with limits, okay, but it's starting with derivative somehow. All right. Right, so let's differentiate a function. Again, we are not differentiating anything numerically, right? We could differentiate it numerically, but we are not doing that. Okay, we are not doing that. So here, see, if I differentiate cos x, again cos x is being treated as a symbol, and I'm differentiating cos x with respect to x, and the result will be minus sine x. Pretty nice, right? That is what it should have, what should have happened, right? Example, differentiating e to the power x square with respect to x, the answer is 2x e to the power x square, right? I think you got this, right? And again, just one more thing, if you want to evaluate this at a certain point, so say for example, if you want to say this is expression 2, okay, and say, and you want to evaluate the result at a certain point, you can always do that. You can do subs and say x comma, say for example, say I want to evaluate this at the point pi, sorry, not x, sorry, evaluate expression 2, right? I evaluated this as at this point, sorry, expression, evaluate expression, sorry, what am I saying? I took expression, not expression, I took expression 2 and substituted x with pi, so I have evaluated this result here. So I can do this evaluation as it suits me, right? I can do that without any issue. All right, right. Now take an expression like e to the power xyz. Now we can do partial derivatives, right? So we can do partial derivatives. Now look what it means, what I'm doing here. So just to show you, okay, before actually doing the derivative, let me show you that we can create unevaluated derivatives. Unevaluated derivative means we can write down the derivative and we can do lazy computation on it. Lazy computation means we are leaving the expression or leaving the function, okay, just for the moment when we need it. Okay, I shall explain that later on. But if I, instead of saying diff, this is the derivative function, instead of saying this, if I call the derivative function with a capital D here, okay, what I get instead is an unevaluated derivative. Right now, this was our expression, e to the power xyz, and I am calculating this partial derivative. Okay, what was the partial derivative? Partial derivative with respect to x, and then with respect to y, but twice, then with respect to z, but 4 times. So it's a del 7, del z4, del y2, del x. So this partial derivative. So partial derivative with respect to x once, then partial derivative with respect to all right. So sorry for the interruption, and I think we are back. Right. All right. So, and the problem is that essentially in our place, the local internet service providers are essentially local monopolies, right? And whenever you have a monopoly in any sector, it's not really bad, not really good at all for the consumers, right? So essentially, I do not really have any other option to choose from. So the ISP can do whatever they want. Essentially, that is really what happens. Unfortunately, especially for me, that the internet connection, the network connection at our home is not good at all. Also, so I cannot even rely on mobile data or things like that. I can't even do that somehow. Right? I don't even cross 1 Mbps on mobile data. That is something I can. So anyway, we are back, and I hope really that. Yeah. So let's again get back to what we are discussing here, right? So this function e to the power xyz, it was a function of multiple variables, right? Okay. So it's a function of multiple variables, and we did a partial derivative on this, right? So this was partially differentiated with respect to x first, and then with respect to y twice, and then it was with differentiated with respect to z 4 times. So someone is saying that which version of Python am I using right now? So I am currently using Python 3.8. So, but you don't have to. You can use Google Colab. You can just go to this one. Let me show you. Okay, you can go to Google Colab, just search for this Google Colab. Okay, and you can just go to Google Colab and follow along with this. Okay, Google Colab probably has Python 3.7, I think. Okay, but it doesn't matter really. Okay, so we are right now today we are actually using SymPy, and we are doing symbolic computations. And if you are using Google Colab or Anaconda distribution, if you have Anaconda distribution installed, you are good to go. You don't have to install anything. Okay. All right. So we have that. So we have differentiated with respect to all of this. So now again, this is something you have to understand, that in this one, we are leaving it for a later evaluation, right? So we are leaving it for a later evaluation, which means that we are doing kind of lazy computation here. So this is an unevaluated derivative. We shall see similar things for unevaluated integrals. So instead of calling the diff function, if I say diff, then the derivative is calculated immediately. Right, the derivative is calculated immediately. Here, if I say derivative, then this is left as an unevaluated derivative. And then if I say do it, so essentially this is a method. If I call the do it method on top of it, so this was the expression here. So this was the expression. And on the expression, if I use the do it method, then it is evaluated. So again, the same results. So this result and this result are the same, but only thing is that this has been evaluated after being declared as a lazy function as such, right? Okay, so I think this is clear to understand. Again, we are using symbolic variables and symbolic functions. So if I integrate with respect to x, so for example, I am integrating cosine x with respect to x, the answer would be sine x, of course. It is not asking me for the limits, right? But I can pass in the limits, but it is not asking me for the limits, right? So if I pass in the limits, it becomes a definite integral. Not always. Strictly speaking, this is not a definite integral. This is an improper integral. But here, what I am doing, I am integrating this with respect to x. So I am integrating e to the power minus x with respect to x from 0 to infinity. Now in SymPy, OO, this lowercase oo is a symbol for infinity. Again, just to show you that it could have been done in a different way, I can call this as an expression and say, I can call this an integral and say pass in the whole thing here, show you. Okay, and let's print this expression. See, this is again very similar to that derivative thing, okay, that unevaluated derivative thing. So if I say that, it shows me the integral but without evaluating it. So this is essentially the integral of e to the power minus x with respect to x from 0 to infinity. So I have that, and with that I can call the method do it. On the expression I can call the method do it, and if I do that, of course it evaluates the result, it becomes 1. So I can do all these things in this way. Okay. Now you might say, what is the advantage of things like this? What is the advantage of keeping something unevaluated, right? Okay, the advantage is that sometimes what happens, you have this integral, but you might want to do some other things with it. Maybe you want to multiply some values with it, multiply something. Okay, so you can manipulate this expression as just another expression, right? And evaluate something like this. So for example, if I say 2 star this, okay, then this becomes another expression. So like that. So essentially you can treat this as an expression and evaluate this later on. Okay, but again, if you want to evaluate this later on, then only do this, otherwise just do the integrate. Okay, got it, I think. So this is again, this is evaluated in terms of gamma function. So this is e to the power minus x square, again integrated from 0 to infinity. Okay, the result is root over pi by 2. Okay, so if I integrate it from negative infinity, so this is negative infinity minus oo. Again, oo stands for infinity in so small oo stands for infinity in SymPy syntax. So this is, if I do that, then this is going to be root pi. All right, so I can do this integration. Again, I could have done this separately by using the expression method here. So I could call this another expression, and I could call it, I could say integral and pass in the whole thing. So again, while doing definite integral or other integral, so again, this is not a definite integral per se, as per the definition in mathematics, right? This is an improper integral, but we are saying integrations with limits, right? We're not calculating the antiderivative here. Okay, so again, we are integrating with respect to x when x varies from negative infinity to positive infinity. And if I print the expression, so this becomes just like that. And I can, at any point, I can evaluate the expression by saying, I can calculate the integration by saying by calling the method do it on top of it, right? Just like that. So I think this is understandable. Now of course we can do double integrals, right? So just to show you what this is, I'm just going to call this expression equal to, well, let me just print this. Okay, this is this double integral, right? So again, you can see that this might come in very handy, right? Because you people in control system engineering, you are actually using quite a lot of integrations, right? In signal processing, you also did quite a lot of integrations, right? Double integrations, namely. So you can do this very easily. Okay, someone is asking, how can I compute the sine and cosine of a matrix? If you want to do that, you probably should look for Numpy. Okay, so I made a tutorial on Numpy. Please go back to that. Okay, so essentially what you are probably looking for is numerical computation. So if you are trying, if you have an array, and on top of that, if you want to calculate certain certain functions, okay, where the argument is an array, you are looking for, what you are looking for is Numpy. Okay, and we made a tutorial on Numpy. Please go back to that. You would see that we actually do this kind of things. So if you are doing numerical computation, if you want to do array computations, Numpy is the best thing that you can use. But SymPy does have the ability to deal with symbolic matrices and arrays, but we are not going to look into that, at least today. But we might, actually we shall come back to that later on while doing control system engineering with Python. Okay. All right. So this is again that integral, and let's evaluate this integral. So again, the same thing we shall do here. So I shall say expression, and we shall say do it. Okay, that's pi, right? Fantastic, right? Okay, there is another one, for example. Again, this is a pretty big, nasty looking integral, right? And again, we are integrating with respect to x. This is a simple integration here, and we're just doing the same thing. Let's do it, and this is the result. You can see how elegant this is. Okay, this can do these things very easily and without any hassle. Again, there is just another integration. Now here, this is just an example where the, so again, what we are doing here is an indefinite integral, right? Now indefinite integrals in mathematics has a better name. It's called antiderivative, right? So essentially you are looking for the function for which the derivative is this one. So that is essentially the indefinite integral, right? That is what we mean by saying indefinite integral. So indefinite integrals are essentially antiderivatives. So now we are looking for the antiderivative of sine square x. So sine x square. So x has a square. It's not sine square x. It's sine has an x square, right? So if I do that, the result might not look like something you already have seen. Okay, the result comes in terms of something called a Fresnel function. Okay, because this does not have a proper antiderivative per se. Okay, this does not boil down to certain primitive functions. So the result is in terms of Fresnel functions and gamma functions and all, right? But again, as long as it can do it, company. All right. And again, results can have certain conditions. Just to show you, this is an integral. Again, some of you might recall that this is the definition of gamma function. Okay, this is gamma n, right? But this definition of gamma function works as long as n is greater than or equal to 1, right? Yeah, somebody is saying this is very powerful. And if you are comparing this with MATLAB, then I would say that the biggest advantage you have while using Python is that it's free and open source, right? So you don't have to pay anybody any licensing fees, and you can do literally anything you want with this. If you make something, you can even sell it without asking anybody. So that's the point here, right? So now, if you recall, this is a gamma function. This is the definition of gamma function. This is gamma n, but this is valid for any real value of n as long as n is positive, right? If n is 0 or less than that, then this definition does not hold true. There is another definition called Euler's definition, which is represented as an infinite product. That is true. That will be true later. But this is the integral representation of gamma function, and this is valid only if n is greater than 0. If n is greater than 0, then this is only valid. Otherwise, it is not valid. So if I now do this integration, of course, if I do this integration, it will show me the result. Okay, what it is showing essentially is that the result is gamma n. Look very carefully. I asked it to evaluate this integral, but it's saying that the result is gamma n if the real part of n minus 1 is greater than minus 1. This is again stupid, but because it somehow could not simplify the condition. But again, the condition is essentially meaning that real part of n is, so you can cancel out minus 1 from both sides, right? So essentially the condition of n is greater than 0. So if the real part of n is greater than 0, then only it evaluates to a gamma function and it becomes gamma of n. Otherwise, it does not know what to do. So it is leaving it as it is. Otherwise, it is leaving it as it is. Unfortunately, I'm having very frequent disconnections today. It seems like my ISP likes to start working on their network whenever I'm teaching something online. Okay, guys, we are back again. Please refresh the stream. Okay, so again, we are looking for this integral of on sine mx in multiplied with sine nx, sine mx, sine nx dx from minus pi to pi. Now you have seen this integral in the context of Fourier transform, right? Fourier series and Fourier transform. We did take this integral, so this is we used that for the principle of orthogonality, and from that we derived Fourier series in our last semester, right? So you know that this has a conditional result, right? This would be equal to pi, okay, if m and n are both integers and they are equal. Otherwise, this is going to be 0, right? But if I run this, it is going to show me some sort of garbage. So let me just evaluate this. EXPR, let's do it again. Okay, the result is going to be utter garbage here. Okay, completely meaningless, some very stupid meaningless thing, right? I don't want something like this. It is showing me so many conditions because it is assuming the most generic case here. Okay, but what if I provide certain conditions for the symbols? Now look at these two expressions here. So I'm saying m is a symbol, okay, and what kind of symbol? This is a positive integer. Okay, this symbol is again a class defined within the SymPy module. So now I'm saying this m is an object of SymPy symbol class where this is an integer and this is also positive. So essentially I'm saying m is a natural number. I'm doing the same thing for n. I'm saying n is a natural number. So now I'm letting SymPy know that m and n are not just some symbols, but they are natural numbers. So they essentially mean that these are non-negative integers, essentially positive integers, essentially natural numbers. So m and n would be natural numbers. So if I say that, okay, the expression looks the same, but what if I now integrate this? What if I now do the integration? See, now it gives me much better result. It says that the result is 0 if m is not equal to n, and the result is equal to pi otherwise. What is the otherwise condition? Of course, when m is equal to n, right? This is what we are looking for, right? So when m is equal to n, the result is pi. When m is not equal to n, the result is 0. We know this from the context of Fourier series, right? So this is pretty intelligent. And again, this package has been developed by pretty intelligent people. Alright, seems like my ISP is trying to stop me anyhow. Right? Alright, so again we are back. I don't know how many more times I have to say this. All right. So now here we are evaluating a certain limit. All right. So, and again, the limit is for sin x divided by x when x tends to 0, right? Of course, the limit is 1. Fine. And again, just like the previous integrals and derivatives, we can write this as an unevaluated function. Okay. So again, I can say something like that, and now this is becoming limit on this. Okay. And by default, it assumes right hand limits. So just you can see that this is being evaluated from the right on cos x like that. So this is cos x minus 1 divided by x, and I am so the limit, okay, when evaluated, it is equal to 0. Okay, but I can choose particularly that if I want the right hand limit or the left hand limit. So I am evaluating the limit of 1 by x when x approaches 0 from the right hand side. So this is going to be positive infinity, and here this is the limit on 1 by x when x approaches 0 from the left hand side. So this is going to be negative infinity. So we can provide these plus and minus as strings after the limit, and it will be actually doing the computation accordingly. Okay, so we can choose our yeah, I have shown you, right? So someone is asking if I want the limit to be from the negative side. Of course, from the left hand side we can actually just put this, right? All right. So if I want a left hand limit here, say if I say something like that, of course this is going to be a left hand limit, and if I evaluate it, of course this is also going to be 0, right? All right. I think that's understandable. All right. Okay, someone is saying, can we calculate the fractional derivatives? Unfortunately, no, we cannot calculate fractional derivatives, right? I do personally work on fractional derivatives, and you cannot, unfortunately, calculate fractional derivatives symbolically. And as far as I know, there is no software, not even Mathematica, can do fractional derivatives symbolically, right? But I wrote certain packages to do fractional derivatives symbolically using Python, numerically using Python. But if you're looking for fractional derivatives and integrals, namely the different integrals, to the best of my knowledge, there is no package that can do it symbolically. You have packages in MATLAB, you have packages in Mathematica. Those can do it numerically. We also developed a package in Python that can do it numerically. But for symbolic computations, we do not yet have packages that can do those things. But for fractional derivatives and integrals, you can write down the expression and you can try to evaluate those things. And for some things, it works because the Matthew function is there inside this. And unfortunately, the Mittag-Leffler function is not there in SymPy. So you are missing out from that. So if you have exponentials or sines and cosines like that, you end up with Mittag-Leffler function. So you won't have that. Yeah, unfortunately, it's a shortcoming, right? Of course, if you are working on fractional derivatives and integrals, you know that doing the symbolic computations is not that easy. Okay, and there are so many gotchas. Again, if some of you did not understand what I just said, forget it. Okay, all right. So again, just one more thing: if you are doing different integrals, doing it numerically is possibly your best choice. Symbolic computation is not probably your best choice here. All right. Now, say I want to expand certain things. Now, of course, we have series expansions, okay? And now this will be a Taylor series, okay? Say if I want to expand, let me expand the most popular thing. So now this expression is e to the power x, and I'm expanding e to the power x with respect to x about the point 0, and I am considering my remainder to be of order 8. So this is the expansion. Okay, now you already know this is the Taylor series expansion. Very nice, I think, right? You can combine this. So for example, if I want this expansion to be in, for example, expansion for sine x, same thing. Okay, yeah, no problem, right? Okay, you can add things like that. So I want a series expansion for e to the power x plus sine x okay, with respect to x at 0, okay, and I want the remainder to be of order 8. So essentially I'm going to going up to order 8 on the proper factors here. Okay, you can have those expressions like that. All right, and we can also evaluate the series expansion at certain other points. Okay, so maybe I don't want to evaluate at 0, maybe I want to evaluate this series expansion at a certain other point, right? Again, we are doing Taylor series expansion. So if my initial point about which we are doing the series expansion is something other than 0, then this is a syntax. So this is again a keyword argument that we are essentially passing in. Okay, so again, so that this is the series expansion, no problem. So this is the series expansion about x equal to 6 for e to the power x minus 6, for example. All right, so again we can just directly say the series expansion. So this is the SymPy function sine x, and on top of that I can call a method and I can call the series expansion on this, okay, about x equal to 0 and up to a point where the remainder is of order 10. I can do that. I can expand cosine series, for example. So this is the expansion for sine x, this is the expansion for cosine x, okay. And just one more thing, this is the expansion for e to the power ix, for example. So this is e to the power ix, right? I is the complex unity. I can do that. But now look very carefully, this is sine x, this is cosine x. So again, cosine x plus I sine x, that's e to the power ix because of Euler's formula here. So I can verify that even, right? So this is cosine x plus I sine x, but expanded in terms of series expansion. But look very carefully that this expansion and this expansion, they are identical. So this is just showing you Taylor series expansion here. Okay, all right. So I think that part actually takes care of itself. So if you want series expansion, you can have that. Okay, again, everything is symbolical for the most part here. All right. Now, in SymPy, you cannot check equality of two symbolic variables with double equal to, right? You cannot check the equality of two symbolic variables with double equal to, right? So if I say x equal to x, okay, it might say true, but it is not a mathematical true. Okay, so this is not an equation. Okay, this will become, if I say equal to in double equal to in SymPy, it would be an identity. Okay, it won't be an equation. So instead, if I want an equation, that symbol would be EQ. So you are going to use this EQ class from SymPy, and if you write down two expressions, in that case they will be now equal to in the sense of mathematical equality, not identity. All right, so this is now going to be treated as an equation, not as an identity. So for example, if I say EQ x square comma 1, then this is going to be treated as an equation, not as an identity. So this is not an identity x square equal to 1. Instead, this is an equation x square equal to 1, which is valid for certain values of x. Certain values of x. And what values of x? In order to calculate that, we use the function solve set. If I use the function solve set and evaluate this, it gives me the set of solutions for that expression. What was the expression? The expression was an equation which was x square equal to 1, and I calculated the solution set, so which was minus 1 and 1. Okay, let me show you another equation where the result is the same thing. So essentially we are writing x square minus 1 equal to 0. That's the equation. Okay, and we are solving for x. If I do that, again the same result will appear here. Another example, sine x minus 1 is equal to 0. Okay, so sine x equal to 1. So if I solve that, the result is 2n pi plus pi by 2, where n is any integer, including positive and negative integers, including 0, right? So that's the solution. You might have studied this in your school, for example, in a chapter called, in mathematics, in a chapter called General Solution of Trigonometric Equations. So this is that thing. Okay, it is solving it generally, right? So the pi by 2 would be a solution. Okay, just like that. And 3 pi by 2 would be a solution, and such and such. So that's not 3 pi by 2, but 5 pi by 2, like that. So you can add any multiple of 2 pi or subtract any multiple of 2 pi from pi by 2, and that will be the answer for this. Okay. Again, we can solve complicated algebraic equations. This is an algebraic equation like x cube plus 2x square plus 4x plus 8, and we're equating it to 0, and we are solving it with respect to x. Of course, the answer would be 2 minus 2i plus 2i. Fine, no problem with us. So again, there is another question. For example, I want to evaluate this. So for example, I want to solve this. Sine x plus cosine x equal to 1. What are the solutions? Again, this might give you a condition like this. For example, this has a solution when x is equal to 2n pi, so multiple of 2 pi, where n is ln. So essentially n is a positive, negative, any kind of integer including 0. And this is a set, of course, and this is in union with this set. So any of these solutions will work. Okay. Of course, sine x plus cosine x is equal to 1 when either of these is equal to 1, when cosine x is equal to 1 or sine x is equal to 1. So cosine x is equal to 1 when this is true, and sine x becomes equal to 1 when this is true. So just like that, it gives you the solution as a set. Okay, and that is why the function you are calling to calculate the solution is called solve set. So it stands for solution set, right? So solving and returning a set. All right, so I think we are done for the most part, right? And we are going to end our discussion with a small discussion on solving ordinary differential equations symbolically. Okay, so and again, just one more thing, we are not going to jump into Laplace transform today, because in one of our earlier classes we did discuss how to do Laplace transforms, inverse Laplace transforms, and so you should probably go back to that and you will see that. All right, here, so now just look at this. Now of course, if I do not use this f and g are going to be generic symbols. Now instead of saying that f and g are just generic Python symbol, generic SymPy symbols, I am saying that f and g are instead functions. So f will be a function name and g will be another function name. So now they will take variables and they will be treated as functions. You will see what I mean, right? So if I treat f and g as functions, so if I differentiate that, what I get is the derivative of fx. So this is again a symbolic representation of derivative of fx. Now fx is not carrying any predefined function, but instead it's a generic function that is actually being represented as fx, right? So fx like that, right? Got it. Now look at the differential equation. So look at this one. So this is, what does this one mean? This one means that I am differentiating fx with respect to x twice. So this is same as saying this. Okay, we are differentiating fx with respect to x twice, subtracting twice of the derivative of fx and adding 3 times fx, and that is, we are making that equal to sine x. So if I write that, okay, this is d2fx dx2 because of this. See, it's a second derivative of fx with respect to x, minus 2 df dx plus 3 fx, and that's equal to sine x. So that is the differential equation we have represented. Just keep in mind that since f and g are functions, f is a function here, we have to predefine that using a condition within the symbols function here. Now here the function is dissolve. So if I say dissolve, it will solve the differential equation. And now we are looking for fx. We are trying to figure out what function fx there is for which this is the solution. And now this is going to give you the general solution of the differential equation, right? So both, okay, both the complementary function and the particular integral will be added and it will be represented as a general solution. So if I do that, so this gives you the general solution of the differential equation. Of course, it's a second order differential equation, second order ODE. So of course, there will be 2 arbitrary constants. So we have 2 arbitrary constants, C1 and C2. But again, sometimes you might not want that. Sometimes you might want to do this computation, do this numerically. Okay, someone is saying, what does this one mean? This one means that I am redefining the variables f and g as function symbols. Okay, symbols have different types of meanings here. Okay, just to show you what I mean, if I say type x, x was a symbol, see, so x here was So we defined x. So again, just you have to go back to the very beginning here. So x is just a core symbol, basic symbol, right? It's a basic symbol. So x is a basic symbol. For example, it will be acting as a variable, right? But again, if you go back to a previous point here, now we again use a symbol class to define a special class, a type of symbol here. This is again symbolic mathematics. We use this symbol class to define a very specific class of symbol. So m, look at this one. M and n were symbols, but these were integers and positive integers. So we imposed a certain conditions on the symbols, right? So if I look at that type of this, so if I say type m, okay, so again this is again a SymPy code symbol, but this has certain conditions. So if I say, for example, recall that m was a positive integer, right? So just go back. If I say x greater than 1, okay, but what happens? If I say x greater than 1, nothing happens, right? So if I say m greater than 1, okay, it does not evaluate anything. But okay, just keep in mind that one more thing. Let's say it's just remember this is a special kind of type of symbol. So if I say type f, okay, so see, this is no longer a SymPy core symbol. So look at x. X is a symbol, right? So if I say f, if I see the type of f, you will see it's not a SymPy core symbol, but instead it's a SymPy core function. Okay, what kind of function? Undefined function, because I want to leave it as an undefined function. Okay, so in order to do that, you are just calling this. Again, this is just a syntax you have to remember. Okay, because whenever you are defining differential equation, remember this fx, you are not predefining it, you are trying to calculate it, right? You haven't evaluated, or rather you haven't predefined fx. While solving a differential equation, your objective is to calculate fx, right? Your objective is to solve for fx. So you leave it as undefined function. So we haven't defined the function yet. So that is the purpose, and that purpose is resolved by this. Okay, got it? So on fg, again, this is a very crude syntax. You can just say f like that, okay, and you can write another one and define g as a symbols. For example, that would be also fine. So f and g are functions like that. Okay, just to show you, same thing will happen here. All right. So again, because the point is that you want to evaluate for fx, you want to calculate something for fx, right? But you don't want to pre-assign it, because the solution is going to turn out to be as a function of f, right? So that is what it is. All right. Again, let's write down another differential equation. So again, we are differentiating fx with respect to x again twice, and then this is the differential equation. So this is essentially d2f dx2 plus 9fx, that's equal to 1. And again, if I want to solve it, that's the solution. Again, it's a second order differential equation, and as such, the solution has 3 constants of arbitrary constants. Yes, so if you want to define an arbitrary function, in that case, you want to use that expression. Okay, but if you want to define any expression, okay, and treat it as a function, you don't need to do anything. Look at this one. At the very beginning we did this. So cosine x plus 1. So if this is your function, you don't have to say anything, right? So this is your expression. Okay, but this is not an arbitrary expression, right? But when we are solving differential equations, fx is an arbitrary expression, right? Right? So fx is an arbitrary expression, so that is treated as a function, for example. I think you got that point, right? So let me just do just one more thing, just to make sure that we are doing okay, just to make sure that the discussion is complete somewhat. Otherwise, I don't think it becomes complete, at least in my context, right? Let's do Laplace transform. Okay, I won't be doing Fourier transform here, but you can also do Fourier transform. Just go to the sympy.org website. you will see everything. Okay, so let's do Laplace transforms. And of course, our variables would be s and t, right? T would be the time domain variable, s would be the frequency domain variable, right? All right, let's do a Laplace transform. So of course, the function is Laplace transform. Everything is being called from SymPy. So Laplace transform of, say, sine of t from with respect to t. Okay, and the variable that I want to end up with, so this is the frequency domain variable, that's s. If I do the Laplace, now you would see that it shows me something very weird. Okay, it says 0, true. Again, these are showing me the conditions for convergence of Laplace transform, because I told you Laplace transform does not converge automatically. You have to put certain conditions, impose certain conditions on the real part of s for that Laplace transform to converge, right? So that's called the region of convergence. 2 points to note here is that the Laplace transforms defined in SymPy, also in Mathematica, also in MATLAB, they are all unilateral Laplace transforms. Okay, because Laplace transforms are often used, and most of the times used in the context of causal signals and causal systems. So you're essentially starting from t equal to 0, right? So again, there is no point of treating these Laplace transforms in bilateral nature, right? So all these Laplace transforms are unilateral in nature, and so if you want to get rid of these conditions, because of course for unilateral Laplace transform, the convergence, I did not tell you the condition for convergence, because for unilateral Laplace transform there is a particular set of convergence. Yes, you can do the integration, absolutely you can do that, but there is just one more thing. You can say no const equal to true, and whenever I'm doing Laplace transforms, I just write no const equal to true, so that it does not bog me down by writing down the conditions and everything. Okay, but you can always do the computation, you can always do the integration. Just to show you that you can do this, so you can do integrate sine t multiplied with e to the power minus s star t. That's the integral, right? And we are integrating from integrating with respect to t from 0 to infinity. Okay, that is how we define Laplace transforms. Now if I do that, it will see what happens here. It shows me certain conditions under which the result is not valid. Okay, so if I integrate this, this is showing me that the result is 1 by s square plus 1, where the argument of 2 when the argument of mod of argument of s into 2 is less than pi. So essentially it means, how can I tell you this? Essentially it means the region of convergence is to the right hand side of s equal to 0, a real part of s equal to 0. So again, this is given in terms of the argument of the complex number s. Okay, and if you just do that, so the region of convergence will be, of course, evident. So you can actually do that here. Okay, so the same result, 1 by s square plus 1. Okay, otherwise this does not converge. All right, so again, let's do Laplace transforms a few more. Okay, let's see, what about, say, e to the power minus a star t star sine omega t. Okay, and while we are at it, let's multiply a t with this, who knows. So we are calculating the Laplace transform of t e to the power minus at sine omega t. This will take a second, and that's the answer. I did write omega, and it did write omega for me. All right, that's good and all, but we also know that we can use inverse Laplace transforms to solve differential equations, to calculate the response of linear time invariant systems, continuous time linear time invariant systems, right? Say we have a transfer function. So say g is a transfer function. Say this is 1 by s plus, say for example, let me write down a simple thing, s plus 1 by s plus 3, who knows. Okay, 1 by s plus 3, just showing you a very simple crude example. The Laplace transform of the input, I know the Laplace transform, maybe I want the step response of this system. So the Laplace transform of the input would be 1 by s, because I already know that the Laplace transform of the Heaviside theta function or the unit step function is 1 by s. Then what is the Laplace transform of the output? That's just g into x. Again, this is not the most efficient way of doing it. I shall teach you the efficient way of doing it, but this is one of the ways in which you can do it. So now that's your output, but you don't want y, but instead you want small y. What would be the small y? That would be the inverse Laplace transform. So inverse Laplace transform of y, and your variable in the frequency domain is s, and you want to come back to your variable in the time domain. So let's do that. So let's print it. Okay, I did not print it, unfortunately. Let's print it. Okay, the answer is this. And of course, this theta t, again, this software has been developed mostly by physicists, and the physicists call the unit step function to be theta t. It's called Heaviside theta function, named after Oliver Heaviside. Although Oliver Heaviside was an electrical engineer, you get the point. Okay, you can just do simplify. Simplify on this. Okay, it did not, right? Factor. Maybe I did not want this. You get the point, right? Again, this is a symbolic expression. I can do all these things with this. The point being, the answer is this. This is the result. Okay. And in any case you want to plot this, you can just very easily plot without saying so many things here. You can just say plot y. This is pretty easily done. If you just say plot y, it does plot it for you. But again, this plot is kind of crude because it does choose the limit here arbitrarily for you. The upper, everything has been chosen arbitrarily. Again, this is using matplotlib to plot it, but if you are doing it numerically, we would have more, what should I say? We would have more control over the result, more control over the plot here. Again, all right. Just for the kicks and giggles, let's convert it to a second order system. Let's say I have a second order system. So it's a x square plus, say for example, say 0.5. Let's say x square plus s plus 1. Say it's a second order underdamped system, and I'm going to teach you that later on. And I'm going to solve for the solution, solve for the step response. Let's see how long it takes. Okay, it did calculate everything and made everything so cumbersome, right? The solution is so nasty here. What if I do simplification on this? Will it work? If I call simplify on this. I think it should work. Yeah, that's the result for you. Okay. So in terms of Heaviside theta function, of course you have ut everywhere, right? So this is your ut. Okay. So that's the solution. That's the inverse Laplace transform here. Okay. So you have a solution. Someone is yes, and someone is saying, are we going to calculate these sort of things manually? And yes, I'm going to teach you that in the next class. I mean tomorrow. And this is not that difficult. And let's plot it. Let's plot it. Let's see what SymPy does for us. And that will be the end of today's discussion. I'm not sure why it's taking so long. Okay, yeah. So this is quite easily it can be seen that it is an underdamped system. The response kind of overshoots its final value and then again goes back. And all right, so that will be the end of today's discussion, and we are going, so essentially what you can understand is that you can take the help of your computer while doing your engineering, right? You don't always have to do everything manually, right? Even though I'm going to teach you how to do these things manually by hand, but you can always use your computer at least to verify your manual results. You don't always have to ask me for the correct result, right? Remember, I had to call the simplify function on here, right? Otherwise the result looked pretty bad. Alright, so we are done with today's class, and you have seen the symbolic capabilities of Python. And that will be the end of today's discussion. And if you have any query later on, you can always ask me. I shall give you the notebook as a Google Colab notebook, and that will be in the video description, and I shall also email it to you. So again, you can import this file into Google Colab and you can just follow along with me, right? So that is the end of today's discussion. Feel free to ask any question that you might have. Otherwise, we're going to end our discussion today here. Thank you very much for being here. And we had quite a few interruptions during our classes here. And here we have, and on the next stream on Python, we are going to discuss SymPy. Okay, so SymPy is used for scientific computation. So we would do many of these things, but numerically. All right. So thank you very much for being here. I'll see you tomorrow with control systems. All right. Goodbye and stay safe.